Okay, so this talk is going to be focusing on programmable packet scheduling at line rate. Again, this is joint work with folks at MIT, Barefoot, Cisco, and Stanford. Now, the motivation for this is pretty straightforward. It's this fact that as a network operator or a researcher, you basically have no hope of deploying a new scheduler in a production network today. The reason is the switch scheduler is baked into the hardware on a switch, and modifying the scheduler or deploying a new one requires you to talk to your vendor and wait for the next generation of the hardware to see it in production. Now, I just spoke about programmable switching chips, so why doesn't that solve this problem? So to answer that, let's look again at one of these switch pipelines. And over time, different aspects of the switch pipeline have become more programmable. For instance, the RMT work from Stanford showed how to make a programmable parser by using, getting the programmer to specify the protocol format for the parser and then recognizing that protocol format. As for the ingress and egress pipelines, the RMT work showed how to make forwarding tasks programmable, and the domino work that I just presented talks about stateful algorithms like AQM. But in the midst of all this, one piece is just fixed, which is the queue and the scheduler. And even today, if you look at a switch, you get some combination of deficit round robin, strict priorities, and rate limits. And you can change parameters in these algorithms, but you can't change the fundamental scheduling logic. So why has programmable scheduling eluded us so far? There are several scheduling algorithms, but there's little consensus on the right abstractions that pervade all these algorithms. If you look at any other aspect of the switch that is programmable, it's because there are good abstractions, or at least some abstractions, for those functionalities. So for instance, parse graphs capture a variety of protocol formats. Match action tables capture a variety of forwarding policies, and packet transactions capture many data plane algorithms. There's no such abstraction for scheduling. Now, this is a further problem in this case of high-performance switching because the scheduler has very tight timing requirements. So typically, you want to be supporting one NQ or DQ, one NQ and one DQ every clock cycle or every nanosecond. What this means is you can't simply punt on the problem and throw an FPGA or CPU in the fast path because it just won't meet performance. So what we need is an expressive abstraction that also runs at line rate. So to get at this abstraction, let's look at what the scheduler does. Fundamentally, it does two things. It decides on the order in which packets are sent. This is for work-conserving schedulers like weighted fair queuing, FCFS, and so on. It also decides on the exact time at which packets are sent for non-work-conserving schedulers like token bucket shaping. Now, if you're going to build a programmable scheduler, you need flexibility in both of these attributes. So how would you go about doing that? So here's a strawman design. Packets come in. They're classified by some classifier into a bunch of FIFOs, one for each flow. And then there's an arbiter sitting in front of these flows, which picks the next flow to transmit either based on the flow order or a particular absolute time at which a flow needs to be transmitted. Now, the problem with this design is there's very little time on the DQ side. If you look at 100 gigabit per second line rate at the smallest packet size, you need to support a DQ every 4 or 5 clock cycles. What this means is that the programmability has to be squeezed into those 5 clocks because soon enough you're waiting to do this for the next packet. Instead, is there a way to do this on the NQ side where potentially you have much more time all the way from when the packet was transmitted at the host until it's received at this switch with the scheduler, right? So our abstraction does exactly that, and here we exploit the observation that in many practical schedulers, the order of packets that are already buffered in the system doesn't need to change relative to each other. So put differently, when a packet comes in, you can determine its location in the scheduling order, just drop it in that location, and you never have to move around packets relative to other packets that are already in the buffer. So an example is, for priority scheduling, this order is determined by the priority of the packet. For first come, first serve, this order is determined by the arrival time. Now, a natural implementation for this is a push in first out queue, which is essentially a priority queue data structure where packets are pushed into an arbitrary location based on a rank, which could denote the scheduling order or scheduling time, but dequeued from the head. So this is what it looks like. You have a sorted array of packets based on rank. Let's say packet with rank 8 shows up. It's dropped in between 9 and 7 here, and packets go out from the head. So how do you build a programmable scheduler on top of this small building block called a PIFO? So if you look at the PIFO, the only part that's really programmable is the way packet ranks are computed within the PIFO, right? So to program the scheduler, you just program the rank computation. And what exactly do I mean by programming the rank computation? I quite literally mean you can write an arbitrary program to compute the packet's rank. So this is just a program that I made up where you look at a packet's flow, there's some state t, that's some key value store on flows, and you use t of f plus the packet length to determine the rank. And this is sort of the key modularity in the design. There's the fixed part, which simply enforces ranks in this PIFO, and there's the programmable part, which computes these ranks. And the programmability is on the NQ side, so you have a much larger time budget to actually carry out these rank computations relative to putting some programmable logic on the DQ side. Okay, so where do these two paths fit in the context of a switch pipeline? So let's bring up the pipeline again. The PIFOs replace the scheduler, the existing scheduler, and the rank computation runs on the ingress pipeline. And how do we run it on the ingress pipeline? We express it as a packet transaction, which is something I spoke about a while ago. And this allows you to spread the rank computation across the entire ingress pipeline. So let's see a few examples of this at work. The first is fair queuing, and we're looking at the virtual start time fair queuing implementation here. So the code is straightforward. For a packet, you compute its flow, and you set the virtual start time of that packet in some idealized fluid model to the maximum of the current virtual time and the finish time of the last packet in that flow. You update this finish time accordingly, and you set the rank to this virtual start time, and the PIFO just enforces that rank. So that's a work-conserving algorithm. Now let's look at a non-work-conserving algorithm like token bucket shaping. The code here is a little more involved, and it has three components. One is there's some logic to track how tokens are updated at a particular rate and capped at some size. Again, tokens are decremented to account for packet transmissions. Second, the packet send time is either the current wall clock time or some time in the future when it would have made up the shortfall in tokens. And third, this absolute wall clock time at which the packet is supposed to be sent out becomes the packet's rank in the PIFO. Okay, so those are examples of rank computations running on the switch. As I mentioned earlier, one of the advantages of this model is the rank computation can actually run anywhere in the network, all the way from the end host where it was transmitted. So let's see an example of that. So let's compress this pipeline down onto the switch, and let's introduce an end host. And let's say the end host runs the rank computation for shortest remaining flow size. So here, for a given packet, you track its flow, and for the flow, you use TCP acknowledgements to compute the remaining flow size. So this is at the core of algorithms like pFabric, and in general, this is theoretically shown to be optimal for minimizing flow completion time. Okay, so far I've looked at algorithms that are all implementable using a single PIFO. And common to all these algorithms is the property that the relative order of packets that are in the buffer doesn't need to change even when new packets come in. So there are algorithms that are beyond this restricted capability that a single PIFO provides. And a canonical example of these algorithms is hierarchical packet fair queuing. More generally, this applies to any hierarchical algorithm, but for concreteness, let's look at HBFQ here. So this algorithm divides capacity of a link between two classes, say red and blue in some ratio, and then recursively between flows within each class, A and B and C and X and Y, right? So let's see why this is beyond the ability of a single PIFO. So this is the scheduling order at some instant in time. Let's say A1 shows up, which is the first packet from flow A. Now we need to satisfy two constraints here. First, Red and blue need to share in the ratio 1:1 because their weights are equal. So red and blue need to alternate in the departure order. But within the red packets, A has a much higher weight than B, so A should move to the head within the red packets. So the only way to do that, given the current state of the queue, is to drop A ahead of all B packets, but move the B packets around relative to the X and Y packets that are already in the buffer. So that operation that I just showed you is beyond the scope of a single FIFO because it requires you to reorder these packets that are already in the system. But it turns out we can implement these hierarchical schedulers using a hierarchy of FIFOs. And our next abstraction is a tree of FIFOs, which allows us to express such algorithms. And this tree actually is quite isomorphic to the hierarchy itself. So the root of the tree is a FIFO that arbitrates between two children FIFOs, red and blue, and each of the children FIFOs store the actual packets themselves. Okay, so what happens on the NQ and DQ? When a packet, say A1, shows up, the class for A alone is enqueued into the root, and the packet A is enqueued into the child FIFO. So this is what ends up happening. Right? So again, each of the FIFOs maintains the right scheduling order for the scheduling algorithm at that level of the hierarchy. Now on the DQ side, we start with the root FIFO, pop that, we get a reference to the blue FIFO, so we chase that pointer down, go to the blue FIFO, pop that, we get X1, and at this point, X1 is a packet, so we just ship it out of the switch. Right? So by chasing these pointers starting from the root on a DQ, we're able to schedule packets using this tree of FIFOs. So it turns out that using both a single and multiple FIFOs, we can express quite a wide list of scheduling algorithms. I'm not going over these in any detail, those are in the paper. But more importantly, there are algorithms that we can't do with even a combination of FIFOs. And the most important class of those is algorithms that do shaping on the output side. Basically, as packets come out of the system of the scheduler, if you want to rate limit the rate at which packets are dequeued, that can't be done in the system because all our programmability is on the NQ side. Okay, again, the details are in the paper. So this is all well and good, but is a FIFO actually feasible in hardware? Because our goal is to run this at line rate. So we set out with some performance targets that are typical for a shared memory switch, like the Broadcom Trident used in many data centers. So these are some concrete numbers. It has a 1 gigahertz clock rate for the pipeline, with 64 ports running at 10G, about 1,000 flows, 60,000 packets. The important thing with a shared memory switch is the scheduler hardware is shared across all ports. And so even the FIFO hardware, which basically is just a different scheduler, is also shared across all ports, and we don't need to further multiply any area numbers that we get by the number of ports. Okay, so how do we go about building this FIFO that can support up to 60,000 packets, or more generally 60,000 elements? So a naive solution is this large flat array, which is sorted by packets or elements, and when a new element comes in, you compare it in parallel to all these elements, determine exactly where it needs to be dropped in, and just shift the array accordingly. Now, as you can imagine, this is a nightmare to lay out in hardware because you need to compare against 60,000 elements in parallel, and those many comparators are essentially a non-starter. Instead, we exploit this observation that for most practical schedulers, you're really scheduling across flows, not individual packets, and you're implicitly assuming that ranks of packets increase within a flow monotonically because you don't reorder packets within a flow. So how do we exploit that? So our hardware design consists of these two parts. One is a flow scheduler that arbitrates across the head packets of all flows. So it's a FIFO over the head packets alone. And then there is this rank store that's sort of an it's in SRAM, which stores the ranks of packets from the second packet onwards, exploiting the fact that they're in first out order. Okay, so what happens on an NQ and DQ? Let's say you get element from flow C with rank 6 that just gets appended to the back of the rank store. If you get D4, because there's no entry in the rank store, it just goes directly to the flow scheduler. So that's the operation on the NQ side. On the DQ side, you first DQ A0 at this point, then you go back into the rank store, reach out and pull out A2, which you then drop in the right location by appropriately shifting the array. Now if you notice this operation here, you again have to take A2, compare it in parallel to all these elements and drop it in the right location, except now it's feasible because we're doing this over the number of flows, which is about 1,000 as opposed to 60,000 packets. Okay, so this data structure supports one NQ and one DQ per clock cycle, which is per nanosecond. And importantly, it can be shared across multiple logical PIFOs that share the same underlying physical hardware. So this is a characteristic of a shared memory switch, and that's what minimizes the area overhead. And these logical PIFOs are essentially PIFOs that are independent of each other, such as PIFOs running on different ports where the schedulers have nothing to do with each other, but just share the underlying hardware implementation. So we have a provision to do that as well. Okay, so to assess the hardware feasibility, let's break down each of these parts of the PIFO. The rank store is a bank of first in, first out queues. It's fairly well understood as a hardware design for a switch designer, because this is how data packets are buffered in the switch. So while we account for it in our area calculations, we don't spend too much time assessing its feasibility. The flow scheduler we actually wrote as a circuit in Verilog, and we were able to show that it meets timing for around 1K flows on a 16 nanometer industry standard transistor library. It continues to meet timing until about 2048 flows and fails timing at 4096. So somewhere between that is the current limit of our design, though we think we can spend time and optimize it further. The area for this design is about 7 millimeters squared in that library for a 5-level programmable hierarchical scheduler. So these are 5 of those blocks that allow you to do 5-level programmable hierarchies. In context, that's less than 4% for a typical switching chip that has an area of 200 mm squared or more. Okay, so I'll put this work in the context of the most closely related work. The idea of a PIFO itself was first used in theoretical work by Chang et al. In the late 90s to show properties of a combined input-output queued router. Perhaps the most closely related to this work is the universal packet scheduling work that looks for a single scheduling algorithm which can appropriately be configured from some end host mechanism to replay all other scheduling algorithms. So the UPS work shows that LSTF is a candidate for such a universal scheduler by using the endpoint to set slacks in LSTF. By the way, that stands for least slack time first. Okay. Now, we can implement LSTF and UPS using PIFOs, but UPS itself is limited because it assumes fixed switches, so it precludes algorithms where the rank computation needs to run on the switch, such as fair queuing and traffic shaping. It also makes use of a single priority queue, so it can't do things like hierarchical scheduling. Okay, so to conclude, I hope to have persuaded you that programmable scheduling is within reach at the fastest speeds that we know of today. And this concretely has 2 benefits. As a network operator, you get to deploy new schedulers to satisfy different performance objectives depending on what your workloads are. And you can do this without haggling with your vendor as to what scheduler should make the cut in silicon. Now, even as a switch vendor, this design is beneficial because you could take your existing menu of schedulers and simply write them as pieces of software on top of this programmable PIFO substrate. And it's easier to fix software bugs than hardware bugs. Thank you, and I'm happy to take questions.
It's a great talk. I really enjoyed it. My question is, how do you take care of wall clock time? You never kind of mentioned that.
Yeah, so there's a slight difference in how the hardware is implemented when you're doing shaping. So you have to look at the rank on the packet and compare it with the clock before sending it out. So that's where we take care of the wall clock time when scheduling packets for a traffic shaper.
So do you allow the mixing of flows, some of which are token bucket shaped and some of which are work conserving? Can you mix flows in that way?
Yeah, so we can do that so long as the shaping happens on the ingress side before packets end up inside a subsequent scheduler. But we can't do that if you're going to do sort of shaping on the output side after packets are dequeued from the scheduler.
Maybe
I can explain this in.
Okay, maybe last thing, which is how does this differ from a calendar queue? Because the calendar queue would allow you to do many of these things already.
So the PIFO as applied to traffic shaping is exactly a calendar queue.
Okay.
I mean, we just use it because we just use the term PIFO because it captures both its use as a priority queue for work conserving algorithms and these calendar queues that dictate times at which things should go out. But you're exactly right. It is a calendar queue for traffic shaping.
But if you have a calendar queue, you're allowed to skip past, that becomes a PIFO as well. If you're allowed to go past missing dates, basically, you get a PIFO out of it. Anyway, but it seems to me that it's very closely related to this.
Sure, we can talk about this offline. Yeah.
Hi, Han Wang from Cornell. Good work and nice talk. So I see you made assumption that the switch chip is 64 port times 10 gig, which is 640 gigabit. And the switch ASICs that some company are making is 6.4 terabit. So how would you do to change PIFO to scale it up to?
Yeah, so that's a great question. At this point, we don't have a concrete design. What I can say is parts of the design, like the rank store, for instance, they essentially look like a first in, first out queue where you need to support one NQ and one DQ per clock cycle. That part of the design, people know how to scale to a multi-pipeline switch, which is how people build these terabit per second switches, where they have multiple pipelines instead of the single pipeline I showed. So that's, we haven't implemented it, but that's my thinking on how the rank store scales. The flow scheduler itself, we implement using flip-flops. So having multiple ports there is relatively easy because we're already implementing them as flip-flops, where it's much easier to add multiple ports to support multiple NQs from different pipelines. But that said, we don't have a concrete design for that yet. We just think it might be able to scale to those kinds of scenarios, but we don't know for sure.
Okay, thank you.
All right, so let's thank Anirudh and all the speakers again.